So we yesterday we finished the chapter 7 on Hartree-Fock theory, and today we'd like to discuss chapter 8 on density functional theory. I expect that we will need today and next week for this chapter, so I'm afraid that in this year's lecture series we will not be able to go beyond chapter number 8. But as I mentioned before, this is okay. I think we covered the most fundamental and the most important basics, and you have now the prerequisites to fully see the link between the fundamental theorems of quantum mechanics and relevant chemical questions which you might encounter in your daily life as a scientist in the future. The most important chapter in that regard was chapter 6 with Huckel theory, and chapter 7 with Hartree-Fock as the first real mean field application. And now I'm very glad that we still can do the density functional theory chapter, because density functional theory is a very important variant of quantum chemistry, which we now have the opportunity to hear about a little bit more in detail. So let me share the slides. Also these slides, so I will also upload these slides to the Adam directory, so that you can download them for your convenience. That was not a good move. Rotating slides here. A wrong key combination. All right, so as we discussed, right, in quantum chemistry, we need postulate number 1 is about the wave function. So we want some variant, some approximation of this wave function. Then, as we discussed in chapter 5 on the molecular quantum mechanics, that wave function then can be transformed in the electron density and can be used to calculate it, to calculate all sorts of observables. Now, within Hartree-Fock, as we discussed yesterday, the approximate wave function is really a Slater determinant, and that means that results then in this Fock operator, which we discussed yesterday, and that accounts automatically for Pauli's antisymmetry condition. Now, as we discussed, the remaining deviation from the true, the full many-body electron wave function, this is what we call correlation. Okay, and there are various methods that have been devised to deal with the electron correlation. So in particular, I list here also certain abbreviations. So MP stands for Möller-Plesset, and there's a number attached to it because this is perturbation theory. Okay, we're using a perturbation theory to include electron correlation, right? And the order of the perturbation theory corresponds to this number. Another very popular approach, which is typically more accurate than Möller-Plesset, is a coupled cluster theory. Right? So in coupled cluster theory, you make use of a certain truncation of your Hamiltonian with or an expansion. It's called the Trotter series expansion, and this has led to very accurate predictions, and also in the series expansion you can go to higher order, increasingly higher order, and you would expect increasingly better numbers. This improvement in accuracy, predictive power, as you go to higher order, this is not a given in the first point for Möller-Plesset theory. It turns out that MP2 is more accurate than MP3 or MP4. So there was a landmark paper that demonstrated that this series of convergence for MP2 for Möller-Plesset is not confirmed. Right? There's no convergence. And so in that sense, MP2 is typically the best you can get in that series. And people don't go beyond. For coupled cluster, however, we can go to a higher order, and we would expect more accurate numbers. The next step is what is known as multi-reference self-consistent field calculations. This makes use of multiple determinants. So you give a lot more flexibility to your wave function. And then in point number 4, you have what's known as full configuration interaction. This is among the most accurate methods, as well as quantum Monte Carlo. This is another method where you use stochastic Monte Carlo moves in order to optimize your wave functions. And so these methods that are listed here are listed in increasing order of predictive power. And so this is not something we will talk about now, but it tells you, it gives you the keywords of methods which go beyond Hartree-Fock. So these are known as the post-Hartree-Fock methods, okay?
As a note, Anatole, we can only see the first slides. We don't see the slide that you're talking about right now.
Oh no. It says my screen sharing is paused. Why? How about now? It's better?
That's perfect, yeah.
All right. So thanks for interrupting me, Moss.
Is this now the second slide, or?
Yes, this is the slide I was talking about. Right, this is the first and this is the second, right? So these are the methods I just talked about. I hope the recording caught that out. Anyhow, so the point is, these are so-called post-Hartree-Fock methods, right? They go beyond Hartree-Fock in the sense that they tackle this missing part to the full solution, the true solution, which we don't know, right? Or we cannot calculate a priori. I've shown you already for helium, for 2 electrons, people have tried to converge this number numerically to very, very many, to very high precision, many digits. So you can imagine that as you go to more electrons, this becomes harder and harder. And so a priori for any large system, let's say something like aspirin, there is no numerically exact solution to Schrödinger's equation. Right? So we have to contend with these approximations, and then we can always, by comparison to the experiment, we can, of course, assess how accurate they are, or by considering the order in the hierarchy you see manifested in this list, right? So they are ordered by increasing predictive power, right? So as you go from MP2 to coupled cluster on the same molecule, right, you would expect your error to decrease. And then you go to multi-reference methods, so full configuration, interaction, quantum Monte Carlo, your error should decrease. Now, if you observe that your error does not change anymore, you can gain some confidence that you have indeed already sort of converged in the sense of the electron correlation energy. You have converged your description. And so then you would expect a small deviation from experiment. So as I said, this requires then some compute cost. And here you have a cartoon from one of the papers from my group, where you see on the y-axis transferability or accuracy measure, and on the x-axis you see the computational cost, where n corresponds to the number of electrons in your system. And you see the semi-empirical methods such as Hückel, or that go beyond extended Hückel, and more modern flavor of that is this PM7, which you see in the bottom left. It's very efficient, right? And it scales quadratically with number of electrons. Hartree-Fock scales to 4th order, and MP2 to 5th order. And here you see a coupled cluster, single doubles. This is n to the 6, right? N to the 7. And there's a perturbation you can do on that, and that gives you CCSDT, which is more accurate at with very little overhead. And if you do the full expansion in CCSDT here, then you're talking n to the 8 in terms of cost, right? So there is a certain prefactor to this. When you, for instance, remember yesterday we talked about calculating the matrix elements for Hartree-Fock independently of getting the coefficients. So this is a one-time cost which scales with your system size, but you typically do this only once, and then you have the SCF iteration. And so this is just the number of electrons that is being used here, but they might have very different prefactors. So in particular for the quantum Monte Carlo case, formally this method scales only cubically, so it would be better than Hartree-Fock, but it has a very steep prefactor, so it's much more expensive than Hartree-Fock typically, unless you go to very, very large molecules or compounds, so that you can that this cubic scaling really becomes the governing factor in this cost. Now, what you can see also here in this figure is a dot for what is known as Kohn-Sham DFT, KS DFT. And you see that it is well above the diagonal line. And so this is something that means this is something like it looks like a free lunch, right? So you roughly speaking, you always have this trade-off between cost and accuracy, right? So there's no free lunch in the sense that for ever more accurate predictions, for ever smaller errors, you have to invest more and more compute power. But if you consider very smart approximations, you might be doing something in your favor, and you might be able to deviate from this diagonal and to get some additional accuracy gain at constant computational cost, right? So this is quite remarkable, and this is why in 1998, as I mentioned also previously, Walter Kohn, one of the founders of density functional theory, was awarded a Nobel Prize in chemistry. He shared this with John Popel, who worked on, and I would have more discussion about John Popel. Actually, the last chapter in this course is about John Popel's work. But basically what John Popel did was to explore the hierarchy among these different methods, right? How can we go from one to the next method? So these two scientists are really outstanding in their contributions, but as always, many others already contributed. So density functional theory is much older than Walter Kohn. So already Thomas and Fermi and also Slater, they discussed variants of density functional theory, but Walter Kohn pushed this much further. Now, you might think that this is neat, but maybe it's also niche, okay? This is just one chapter in a theoretical chemistry lecture, and so maybe DFT is important enough to warrant a chapter, but it's a side thing, particular exotic thing to chemistry at large. Now, you'd be very wrong with this assessment, right? It turns out in 2014, there was a paper, an overview paper published in Nature on the 100 publications in human history that have been cited the most. And typically citations indicate that something is useful, right, to the community in one way or another. But, so, and it turns out that in the top 10 papers of all times, right, density functional theory shows up twice. Okay, so it's arguably a theory that has a tremendous impact on science, and it is remarkable that so little is known about it, right? I believe because of this simple analysis already, one would have very good reason to include a discussion of DFT already at high school level. It is of such fundamental importance. Now, there are two papers referring to DFT. They are rather technical. They are really used a lot. But the user community, if you think about it, is gigantic. They're not only chemists, there are also material scientists, there are solid state physicists, there are molecular biologists, This is a very, very large research community with very close connections to industry, right? And so this means that there's a real driving force behind the demand for density functional theory, and you can view this as the manifestation of the demand for quantum mechanics, right? This is how important quantum mechanics has become in its implementation, in its variant as implemented through density functional theory, right? So I cannot stress this enough, of course, and so I'd encourage you to seriously consider this. So it's not just chemistry, right? It's these were the 100 most cited papers across all scientific disciplines. All right, in our chapter on the electron density, we discussed already the Hohenberg-Kohn theorem, and in particular the proof. I'd like, just for the sake of completeness, to briefly recapitulate this today. Now, the fundamental assumption is that the electron density, in this case we use a small n, right? Instead of rho, of course you can also use the Greek letter rho, it doesn't matter. N is used more among the physicists because n is typically a density, a particle density symbol, right? And so electrons are particles, and so this is quite common. Now, this n is supposed to be a fundamental property of the system, right? And we discussed how to calculate it already. Now, what's remarkable about it is that it is three-dimensional, right? It's a function of three dimensions, x, y, z, right? You can intuitively, as we discussed, imagine it like a cloud of electrons. Now, that means that this electron density is actually independent. Its dimensionality is independent of your number of electrons, okay? So it's independent of your number of particles, right? So this is the formal, right? The formality, the number of variables in your electron density does not depend on how many particles, how many electrons you put in. It's always x, y, z, right? You can just increase the magnitude, but the dimensionality of this function does not change, right? So as such, it's an extremely appealing function, and as such, it's quite a preposterous idea that this low-dimensional function should contain the same information as your wave function, which depends on 4 n dimensions, so the spin variable and the 3 Cartesian coordinates for every one of your n electrons. Okay, so this is a crazy proposition that the electron density could do this, that it would be sufficient, right? So here again, you see it, we integrate out all 3D coordinates for all the n electrons but 1, okay? So this is a projection, right, onto a low-dimensional manifold, and it is really not at all obvious that this should be sufficient, right? That this is enough to describe the entire quantum mechanics of your system. Right? So this is really, people before Walter Kohn have worked with the electron density, but it's everybody felt not at ease in assuming that this is a complete concept, and that there's no severe approximation taking place when using it. So in the theorem number 1, we can show that the exact many-body electron wave function of this electronic ground state psi, as it is defined by the Hamiltonian, that means by the external potential and the n interacting electrons, that this psi is in a one-to-one relationship with this low-dimensional single particle electron density. If this is true, right, the implication is gigantic. It would mean that all QM observables could be written down as functionals of the electron density. And what I mean by a functional is that you map the electron density to a single number. So typical examples for functionals are integrals. Whenever you integrate something, right, you take the shape of the entire function over the entire domain you're integrating, and it maps to a single number. So this is where the name density functional theory comes from. So the proof is, we discussed the proof already. It follows the reductio ad absurdum. So we presume first the contrary of what we want to show, right? And we then look what are the consequences of that assumption. And if the consequences lead to something absurd, then it means that the original assumption was wrong. And so the opposite must hold. So the opposite of the opposite is then what we wanted to show. All right, so we presume now, and I'll give you as an example, the external potentials of two isomers, just to facilitate your life. Now, these two isomers, ideally, they should have the same number of electrons. So presume, let's say, two constitutional isomers, okay? So what should we take? For instance, butane and isopropyl. So the 2-methylpropane, I think is the formal name, right? I can make you a drawing of that. All right, here you go. Right. So these are the two systems we want to consider. They have two different external potentials, same number of electrons, same number of atoms, and we presume that V1 is the usual butane and V2 is the isopropane, right? Now, we now want to presume the opposite of what we want to show, right? So we want to show that for every electronic wave function, there's only one electron density. And now we propose the opposite. So two different electronic wave functions would map onto the same electron density. So suppose these two guys would have, of course, they have different wave functions, but suppose they would have the same electron density. Right? So that's this electron density n, right? So this means then that if I use my wave function for the isomethylpropane, right, the psi2, and I use this for the butane, right, I would get some crazy energy number, some crazy expectation value, which must be larger than if I use my butane wave function for butane. That's the simple variation of principle. And that is, of course, just my energy of butane, right? Now, with the electron density being the same, it means that the part with the external potential here, P1, one's with psi2 and one's with psi1, right? That this must map towards the same electron density of V1. And hence I can cancel it from the inequality, right? So this part cancels away. And so I have this as an inequality left. I can do the same with by exchanging the indices, right? So then I'm looking at the external potential of my isomer 2, one's with the wave function of butane and one's with the wave function of the methyl propane. And now again, this will be lower in energy when external potential and wave function map. And again, they map towards the same electron density, so I can cancel also this one from the inequality. Now you add these two inequalities, and you will find this inequality here, where you basically have A plus B being larger than B plus A. And that's obviously not possible. And hence, this original assumption here that they can have the same density must be wrong. So they cannot have the same density. Yeah. Now, the second theorem is a kind of a variational principle. So among all possible densities, there is a ground state electron density, which will minimize the functional of the energy, okay, for any given system, right? And this is the electron density, which would correspond to the electron density which you get from the wave function, which has minimized your energy, right? Now, there is a little problem here, which you can see already. We don't really know what is the energy functional of the density. We know what is the energy functional of the wave function, right? That's just the expectation value of the Hamiltonian. But we don't know that for the electron density. So this is the problem. This is so we replaced our wave function by something much easier, but what was easy before was the Hamiltonian, right? And now we don't know the Hamiltonian. What is the Hamiltonian for the electron density? We don't know that. So in some sense, we did like a Hütchenspieler trick. No, we pushed things. We pushed our ignorance from one place to the other, right? But the problem is still not solved, right? Actually, it turns out, and you could call this the no free lunch theorem. It turns out that we know by now that the kind of Hamiltonians you need for the electron density are incredibly complicated. Right? So it's really an open question. What is more difficult, the true wave function or the true density Hamiltonian? We don't know this. All right, now we can use this to define an electronic chemical potential. And the chemical potential is, of course, a key variable, as you know, from thermodynamics. And in our case, this would be the variable that describes what happens in terms of energy as you vary number of electrons, okay? Our particles are the electrons. So the electronic energy can be written as a functional of the electron density implicitly. We don't know this exact functional, but we can write it implicitly. And we denote functionals with these square brackets, right? So this is now the energy, not as a function of n, but as a functional of n, right? So n is your entire function, and E is just a number, and you can think of this as an integral. And it's written in as three terms There's the term with the external potential. This one we know, of course. This is just the classical interaction with the nuclei. But then there's a kinetic energy for the electrons, which we don't know how it looks like. There's some integral of the electron density, and the electron-electron interaction, which is also some integral of the electron density. We don't know this. So again, here functionals are functions of functions. So you have a function typically maps a variable towards its function value, and a functional would map the entire function to a value capital F here. You write this with a square bracket. Integrals are functionals, and they are for any function you will get one functional, but you cannot reverse the thing, right? They are surjective and they are not bijective, right? So you cannot, if somebody gives you the functional value, you cannot reconstruct the function. Right? So if we wish to vary our electron density, we have to make sure that the total number of electrons is conserved. And we can do this in the usual way. So there's a constrained optimization problem, and using Lagrange multipliers is a very common method for solving such problems. So we can write our new functional as a function that contains the unconstrained energy functional as in equation 1, and then we have a bracket here which is supposed to be 0. So what is supposed to be 0 is when we integrate over your electron density, you should get the number of electrons, right? So that would be n minus n would be 0. Now, if you vary your electron density, you still want this bracket to be 0. Right? And so that's why we write this here. And in front of this bracket comes a factor which is known as the Lagrange multiplier. We will see in a second what this is. Now, the variation of a total differential, right? So think about what you did in thermodynamics for your entropy, for instance, right? You write your total differential as a sum over all your variables, where you take the partial derivative with respect to that variable times its variation, right? So this is a simple application of a chain rule. And we want to do this here, right? Only that instead of a sum here, right, we now integrate over the 3D space. So we have a continuous variation in space, and so we use the integral, right? So a derivative of a functional must be an integral over something like this chain rule here, right? And for this, we use also this delta, like the Kronecker delta. This is a notation, right? And so if we want to vary our constrained energy functional, we write this like this. So this is akin to this df now, right? And then we see that this is the differential operator is of course linear, so you just pull this through, and your n here, right? This is just a constant. So this doesn't vary, and you're only left with a variation in your electron density. And now look at this functional derivative of dE is the integral over space, and now we have the partial derivative at every point in space times the variation in that point, right? Here we just keep this integral, and what you see here now is that the variation in electron density is the same. The integral goes over the same spatial domain, so I can factor out our delta n in equation 3. Right now, there's the theorem or lemma in variational theory that for this integral, right, to be 0, Right? We want this to be 0 because our energy should be minimal, right? By the variational principle. For this integral to be 0, this integrand, the bracket here, has to be 0 too. And this means that if this bracket is 0, this means that your mu is equals the derivative of your energy with respect to variation of electron number, right? And we can write this again. If you look up here, right, then this is the external potential, the derivative of T and the derivative of the electronic energy, right? So our chemical potential consists of this external potential and these two terms. This is also known as Euler's equation, right? It's a condition on your variational minimum in your electron density. So mu is this chemical potential, right? And the question is, what are these last two terms, right? The external potential, we understand. These last two terms, we don't. So it's 10 o'clock now. I'd like to stop the lecture with this cliffhanger, right? I hope you can survive the incredible tension that was built up here. And I'll tell you more about this on Monday. Do you have any questions at this point? That's not the case, then thank you for your attention and see you next week.
Bye.
Bye-bye.